Good afternoon, everybody, and welcome to our webinar, Reducing Greenhouse Gas Emissions Associated with Nitrogen Fertiliser Using Nitrification and Urease Inhibitors. My name is Pete Berry. I am the thematic lead for the Crops Management Group within the Climate Farm Demo project, and I'm joined by my colleagues Ben Hague and Christina Baxter. All three of us work for a company in the UK called ADAS, and we're all crop physiologists with an interest in crop nutrition. So if you move on to the next slide, please, Christina. So the main aim of this webinar is to better understand the role that nitrification inhibitors and urease inhibitors have to be used with nitrogen fertilizer to reduce greenhouse gas emissions. We'll split the webinar into three parts. Firstly, an introduction given by Ben Hague about the greenhouse gas emissions associated with crop production to put things into context. And then my colleague Christina will describe the nitrous oxide and ammonia emissions associated with nitrogen fertilizer use and the mechanism by which the nitrification and urease inhibitors reduce these and the impact that that has on greenhouse gas emissions. Then we will finish with a question and answer session to cover any points which you're uncertain about. Next slide, please. So during the webinar, we ask that you keep your camera off and your microphone off. You should be muted anyway, but we really encourage you to ask any questions in the chat and just press on that chat logo and write your question in, and we'll do our best to answer some of these questions, and we'll return to some of them during the Q&A at the end. It's unlikely we'll answer all the questions, and those that we don't, we'll try and answer a few more after the webinar and circulate the answers later. So at the end, we'll have a question and answer session. Continue to put your questions in the chat, but if you want to ask the question verbally, then put up your hand, raise your hand, and we will unmute you and you can ask verbally. Next slide, please. Now, I'm conscious that not all of you will be familiar with the Climate Farm Demo project, so just a very brief background about this project. It's a European-wide project. It is running for 7 years. It started in 2022. It involves 65 partners from a wide range of disciplines, including universities, advisory services, farmer organisations and applied research institutes, as well as NGOs. There's a tremendous amount of activity to engage with practitioners, the farmers and advisors, and help them to reduce greenhouse gas emissions. For example, the target of a project is to achieve 4,500 on-farm demonstration events. So there's a lot of practical activity within this project with the ultimate aim of reducing greenhouse gas emissions significantly by 2030. This webinar is part of many webinars which are taking place at the moment to improve our understanding about how to reduce greenhouse gas emissions in a practical way. Next slide, please. Now, before we start, it would be really useful to find out a little bit more about yourselves with a couple of polls. And we're asking you if you could tell us whether you're a farmer, an agronomist, a researcher, whether you're from industry, or whether you're involved in policy decisions or other. So if you could please say what you are, that will be really helpful. Okay, we can see the results coming in now. So we've got about 40% of researchers, 23% agronomist, 2% farmers, 21% industry, and other at 15%. We'll leave it open for a few more seconds just to get the full responses. I can see we've got 73 people on the webinar at the moment. We've got 53 sponsors in so far. So if you haven't done it, I'll give you a little bit more time just to put your response in, please. Okay, thank you very much. So we've got about 40% researchers, 20% agronomists, and about 20% industry. That's the majority of the attendees today. And if you could load the next slide and poll, please, Ben. So this is really understanding what your interest is in understanding urease inhibitors and nitrification inhibitors. So is it to comply with regulation? Is it to improve nitrogen use efficiency on your farm? Is it to reduce greenhouse gas emissions, or to reduce pollution, or to increase yield and quality, or another reason? So if you let us know what it is for you. Okay, so the majority of responses are coming in as reducing greenhouse gas emissions. That's over 50%. The second most commonly clicked item is to improve nitrogen use efficiency at about 20%. And then we've got other at 16% and low amounts for the other options there. So that's good. The majority of you are joining this webinar to understand how to use these to reduce greenhouse gas emissions. Okay, well, thank you very much. I'm going to hand over now to my colleague Ben, who's going to give some introductory slides about greenhouse gas emissions to put things into context. Thank you, Ben.
Thanks, Pete, and good afternoon, everybody. So as Pete mentioned, firstly, we're just going to go over a couple definitions to make sure we're all on the same page in terms of what we'll be discussing today. So firstly, we're going to be talking about carbon emissions. We talk about these as in terms of carbon dioxide equivalent, and that is to consider the different greenhouse gas impacts of different greenhouse gases. In agriculture, this is mainly CO2, nitrous oxide, and methane, and particularly in arable land, we're talking about CO2 and nitrous oxide. And by talking about greenhouse gas impacts in terms of the carbon dioxide equivalent, we can compare the impact between carbon dioxide and nitrous oxide, whilst considering that nitrous oxide has an impact on global warming roughly 265 times more than CO2. If you move on to the next slide, please, Christina. So this slide gives an overview of the different sources of greenhouse gas emissions in crop production. And these are generally split into three sections. So on the left, you have the embedded emissions, which are emissions brought on farm in the form of fertilizers, seeds, and pesticides. And these are the emissions that are involved in producing these products that are then applied on farm. In the central section, we have emissions, nitrous oxide emissions. These are both direct and indirect emissions. So the direct emissions result from the application of inorganic nitrogen fertilizer, as well as organic material application. But we also get indirect emissions from crop residue decay, and that's after the crop is harvested. The residues left in the land will then decay down and release some nitrous oxide into the atmosphere. And on the right-hand side, we have the carbon dioxide emissions. These are largely related with fuel and energy use, so things like diesel and petrol or grain drying contribute to these emissions. And if you could move on to the next slide, please, Christina. So here we're going to talk about some of the data we've collected within our Yen Zero network, which is a farmer-led network where they calculate carbon footprints for different crop types. And so on the left-hand side, we have the carbon footprint of different crop types expressed as the carbon dioxide equivalent on a per hectare basis. And you can see that the crop types with the lowest carbon footprint are the nitrogen fixing crops. So these are your pulses, your peas and beans, sorry. And then in the middle of the graph, we have the low nitrogen input crops. So these are sort of your oat crops, your spring barleys, and so on. And then on the right hand side, we have what we consider to be high nitrogen input crops. So these are feed winter wheat, oilseed rape, and milling wheat mainly. And the main message from this graph is that carbon footprints are related to how much nitrogen you apply to different crop types. So the best way we can optimize our carbon footprint is to optimize how much nitrogen we're applying to our crops. And if you could move on to the next slide, please, Christina. And so this is a graph we produced using RDN0 data, where we've partitioned the different sources of greenhouse gases for a winter wheat crop. So you can see from this graph, the main message is that most of the carbon footprint for a winter wheat crop is from either the application of nitrogen fertiliser in the form of nitrous oxide emissions, and you can see this is the dark blue segment of this pie chart. This is about 35% of the carbon footprint of a winter wheat feed crop we'd expect to come from the application of the nitrogen fertiliser. And then the second biggest partition in this pie chart is the light blue pie segment. So this is the manufacturer of the nitrogen fertiliser. This takes up roughly 22% of the carbon footprint for this wheat crop. Some of the lesser contributing segments, which also have a significant impact, are the nitrous oxide from crop residues. So this is the green segment in the top left. And we can also see fuel use in operations. So this is the CO2 emissions from energy and fuel. This equates to roughly 17%. And you can see that the production of seed and agricultural chemicals represents quite a minor portion of the carbon footprint for a wheat crop. So it's important to realise that the best way to minimise our carbon footprint is to optimise our nitrogen applications. And now Christina is going to talk through some of the benefits and the modes of action of different nitrification inhibitors.
Perfect. Thank you very much, Ben and Pete. So good afternoon, everybody. So over the next 20 minutes or so, I'm going to discuss the emissions in a bit more detail that are associated with the use of nitrogen fertiliser in arable scenarios. And I'm going to talk about how we can use urease and nitrification inhibitors as a tool to reduce these associated emissions. And I'll also quantify the impact of reducing these emissions on the total carbon footprint of a wheat crop, as an example. So I'll try to explain this slightly complicated schematic, which is illustrating the processes that occur when nitrogen fertiliser is applied to land, and the gaseous emissions that occur on the back of that. So if we start with the application of nitrogen fertiliser, the first step in the process is the conversion to the ammonium positive ion, which is then available for plant uptake. But during this process of conversion to ammonium, some of the nitrogen can be lost through the process of volatilization to ammonia gas. But the ammonium that isn't volatilized can then go through a process of nitrification to form nitrate. And this is also freely available for plant uptake. But during this process of nitrification, we see losses of nitrogen through emissions of nitrous oxide emissions. But the nitrate that remains can then be leached into waterways because it's very soluble, or it can be immobilized into organic nitrogen forms and subsequently broken down to be recycled back into ammonium. Another process that can occur if conditions are more anaerobic or at high levels of water, we can see denitrification of this nitrate, which results in production of nitrous oxide in the same way that nitrification can produce direct nitrous oxide emissions. And denitrification also causes emissions of nitrogen gas as well. So denitrification and nitrification cause direct nitrous oxide emissions as a result of the application of nitrogen fertiliser, but we also see indirect nitrification. We also see indirect nitrous oxide emissions associated with nitrogen fertiliser use, and this can occur in two different pathways. The first being this ammonia gas that's been volatilised can then be deposited back to land to form ammonium, and then through the nitrification and denitrification pathways can indirectly release nitrous oxide. The second pathway is this leaching of nitrate into water sources can also cause nitrous oxide emissions through the process of denitrification. So these are the specific nitrogen pathways that we're interested in and that we'll focus on when thinking about the activity of urease and nitrification inhibitors, and I'll talk about that in a bit more detail now. So I'll start with the volatilisation nitrogen loss pathway, which is of concern when we're thinking about urease inhibitor activity. So urease inhibitor activity specifically is relevant to urea-based nitrogen fertilizers, so our urea and UAN fertilizer forms. So when urea is applied to land, it undergoes a process of hydrolysis where this urea is converted into ammonium, and this is via the urease enzyme. And during this process, which is shown in this simple schematic here, this hydrolysis process where urea is converted to ammonium causes nitrogen, a proportion of the nitrogen, to be lost through volatilisation as it's converted to ammonia gas. And the amount of nitrogen that's lost through volatilisation is very variable depending on the environmental conditions, and I'll talk about that a little bit later. But on average, if we take figures from the IPCC, we consider around 15% of the nitrogen is lost through volatilisation when using urea fertilisers, and around 10% for UAN. And it's really important to note that ammonia is not a greenhouse gas, but it is of concern for air quality issues. And also, as I've just mentioned in the previous schematic, this ammonia can be deposited back to land to form ammonium, which causes indirect nitrous oxide emissions. And around 1.4% of this volatilised nitrogen contributes indirectly as nitrous oxide emissions. So volatilisation can vary widely depending on the environmental conditions, and this is important to consider because we can negate some of these associated emissions from urea-based fertilisers if we apply them in the right conditions. So previous field studies have measured ranges of as little as 4 to as large as 47% of the urea-applied nitrogen lost through volatilisation. And this compares to emissions of around 4% for ammonium nitrate fertilisers, which don't go through this process of hydrolysis to form ammonium. And specific conditions of concern that cause greater volatilisation are dry and warm conditions, high soil pH, and no-till soils can also exacerbate volatilisation. So in the charts here, you can see we've got on the axis here, we've got days on soil. So this is the number of days that the urea-based fertiliser is left on the soil surface. And then we've got the percentage of volatilisation to ammonia. As you can see, the longer the fertiliser is left on the soil surface, the greater volatilisation we see. And this tends to occur in dry conditions, and also can occur in no-till conditions as well, where there's less soil to fertiliser contact. You can also see the impact of soil pH. As soil pH increases, we can see increases in volatilisation, and the effect of soil temperature. So warmer soils are associated with greater volatilisation. In no-till soils, we also tend to see higher trash on the surface, which can contribute to higher soil temperatures. So that's another reason for no-till conditions causing greater volatilization. So as I've mentioned, ammonia isn't a greenhouse gas, but it is of concern because of the issues associated with air quality. And this is because ammonia and its deposition can cause eutrophication of water bodies and also soil acidification. Predominantly, the concern originates from the fact that ammonia can form fine particulate matter in the atmosphere. So this can cause respiratory diseases in humans. So because of this, Europe have set reduction targets to substantially reduce ammonia emissions. And this is very relevant to agriculture because the majority of ammonia emissions are associated with agricultural activity. So, for example, in the UK, we see 90% of the ammonia emissions being associated with agriculture, and 15% of these emissions are associated with fertiliser use. Predominantly, the ammonia emissions from agriculture tend to be associated with the storage and handling of organic materials. But these reduction targets involve policies being implemented across European countries that involve use of best available techniques. So this can include better application methods for applying organic materials so they're incorporated into the soil more quickly. But in relevance to today's webinar, they also involve the greater use of urease inhibitors. And specifically in the UK, we've recently seen a regulatory change where growers are required to use urease inhibitors with urea-based fertilisers if they're being applied after the 1st of April, with this date being it's set because we see drier and warmer conditions in the spring and summer, which are more conducive to higher volatilisation. So the targets for the UK for ammonia reductions are published in our Clean Air Strategy, and our specific targets for ammonia emission reductions are to reduce our emissions by 16% of our levels published in 2005. So that's what's shown in the red line here, and you can see how we've been reducing our ammonia emissions over time. But in more recent years, we've seen a slight levelling off of this reduction, which explains why our government are trying to implement more policies to decrease these ammonia emissions further. So moving on to the activity of urease inhibitors and how they specifically reduce volatilisation. So urease inhibitors work by delaying the process of hydrolysis, and they work by blocking the active sites of that urease enzyme, and therefore they reduce the ammonia emissions. So urease inhibitor actives include MBPT, 2-NPT and NPPT, and so commercial products you see on the market will more than likely include one or more than one of these active ingredients. Because we see high volatilisation in urea-based fertilisers and the loss of nitrogen through this volatilisation, we do see less efficiency in urea-based fertilisers, and on average, urea is around 10% less efficient compared to ammonium nitrate. But with the use of urease inhibitors, the fact that they reduce this amount of nitrogen lost through volatilisation, they do work to improve nitrogen efficiency to around about the same level as ammonium nitrate. So this is a clear agronomic benefit to using urease inhibitors for growers. Work that's been done in field trials in the UK is shown in this chart here on how urease inhibitors can work to reduce the amount of nitrogen lost through volatilisation, and the bar charts summarise work done on 10 winter cereal sites in the UK using the urease inhibitor under the commercial name agrotane, which contains the active ingredient NBPT. So in the red bars, you can see the ammonia loss associated with using urea. So in these conditions, on average, the ammonia loss was nearly 25%. But with the use of the urease inhibitor, this can be reduced to around 5%, just over 5%. In the case of UAN, the average proportion of nitrogen lost was nearly 15%, but with the use of the urease inhibitor, this has been reduced down to around 10%. And you can see on average, the percentage of nitrogen lost through ammonium nitrate is around 5%. We've also done some on-farm trials recently in partnership with BASF to demonstrate the benefit, the agronomic benefit of using urease inhibitors. And this is with their product Nitrous, which contains two active ingredients, which is MBPT and NPPT. So in the first example, we ran on-farm trials, around 15 different trials, where we compared ammonium nitrate application with urea application with this urease inhibitor Nitrous. And as you can see, over these trials, on average, there was no significant difference in terms of the yield for those crops that were, for those parts of the field that were treated with ammonium nitrate and those that were treated with urea and the Nitrous product. In the second example, we tested untreated UAN versus treated UAN with Nitrous Perform, which works in a very similar way to Nitrous. And on average, you can see there's a clear, significant agronomic benefit, as we see around a 0.1 tonne per hectare yield benefit of using the Nitrous Perform product. So what we tend to see with urease inhibitors, because of this agronomic benefit, they make economic sense to growers. So the cost of the urease inhibitor product tends to be covered by the agronomic advantage of improving the nitrogen efficiency of the products and therefore the crop yield. So I've mentioned already that ammonia is not a greenhouse gas, but as we've seen in the schematic I showed at the start, volatilized ammonia deposits indirectly and causes indirect nitrous oxide emissions. And we can quantify the benefit of using urease inhibitors on crop carbon footprints because of this reduction in indirect nitrous oxide emissions. And based on past experimental data, the UK greenhouse gas inventory can apply a reduction factor if urease inhibitors are being used of 70 and 44% when used with urea and UAN respectively. So if we use an example winter wheat feed crop that's had a total of 200 kilos of N applied, and using the IPCC volatilization emission factors, which I talked about in the start, which was 15% and 10% for urea and UAN in terms of the amount of nitrogen lost through volatilization, we can quantify the emissions. So for urea use without a urease inhibitor, the indirect greenhouse gas emissions associated with volatilization in terms of kilograms of CO2 equivalent per hectare is around 175, and for UAN it's around 117. If we apply these 70 and 44% reductions, we can reduce this down to 52 and 65. And then we can show the impact on the total carbon footprint of the crop. So this is considering all those activities that Ben showed in his schematics in the pie chart. This gives us, without the use of a urease inhibitor, just over 2,000 kilos of CO2 equivalent per hectare for urea, and when using UAN, just below 2,000. If we use the urease inhibitor, the reduction in those indirect nitrous oxide emissions can contribute to a total carbon footprint reduction of around 6 and 3%. This is showing the direct benefit of urease inhibitors on the total crop carbon footprint. So that's a summary of urease inhibitors, how they work and how they can impact both air quality and crop carbon footprints. I'll now move on to nitrification inhibitors. So nitrification inhibitors specifically work by blocking the reaction of ammonium being converted to nitrate, so that process of nitrification. And nitrification inhibitors, because both urea and ammonium nitrate fertilizers are converted into ammonium form in the soil and go through the process of nitrification, we can use nitrification inhibitors on both urea and ammonium nitrate fertilizer forms. So this is shown in the schematic here, where specifically the nitrification inhibitor acts in this process of nitrification. And specifically, it's when the ammonium is converted to nitrite. So they specifically work by inhibiting the monooxygenase enzyme produced by the bacteria of the genus Nitrous. And some of the active ingredients that nitrification inhibitors can include DCD, DMPP, and nitropyrin. So essentially, the nitrification inhibitors keep more of that nitrogen in the ammonium form and less nitrogen in that nitrate form. Because of this, we see less nitrification and denitrification of that nitrate to form direct nitrous oxide emissions. So nitrification inhibitors work to reduce those direct nitrification, nitrous oxide emissions. So as with volatilization, we see very varied proportion of nitrogen lost through this pathway, which is influenced by environmental conditions, but on average we see around 1% of the nitrogen lost through this pathway in direct nitrous oxide emissions. And the specific conditions that impact how much nitrous oxide emissions we see are soil moisture and temperature. And that's what's seen in these charts here. So on the left-hand side, you can see the proportion of water-filled pore space in the soil. As this increases, we see a greater amount of nitrification and therefore nitrous oxide emissions. And as the proportion of water-filled pore space increases, we see anaerobic conditions which cause denitrification and can increase nitrous oxide emissions and also emissions of nitrogen gas. This chart here shows work done in the UK to show how nitrogen application timings impact the amount of nitrous oxide emissions we see as a result of applying nitrogen fertiliser. So the coloured dots, we've got air temperature. Here we've got rainfall and then the nitrous oxide emission factor in terms of the percentage of total nitrogen applied. In the coloured dots, we've got the timings 1, 2, and 3, the first being early in the spring and the third being late in the spring and the early summer. So because of the difference in the environmental conditions between these split timings, we see differences in the nitrous oxide emissions. So in the black dots, in the early in the spring, we tend to see cooler air temperatures and therefore lower nitrous oxide emissions. Whereas later in the summer, where air temperatures are higher, this is conducive to greater nitrous oxide emissions. When we partner this with higher rainfall, 7 days after the total rainfall within 7 days after application, we see a higher amount of nitrous oxide emissions. Because only around 1% of the applied nitrogen is lost through this pathway of direct nitrous oxide emissions, there's limited evidence to support an agronomic benefit of using nitrous oxide inhibitors, which makes them difficult to encourage their use on farm because there's no clear economic benefit to growers. And therefore, if we want to see more use of nitrification inhibitors on farm, we're going to need incentives for growers to do so. So the use of nitrification inhibitors in past experimental work has shown to reduce nitrate leaching because of the fact that it's keeping more nitrogen in that ammonium form versus in the nitrate form. We've seen limited evidence in the UK to show that nitrification inhibitor use reduces nitrate leaching. This is due to the fact that when we're applying nitrogen to arable land in the UK, it tends to be in the drier parts of the season. So it's less conducive to high leaching conditions. High nitrate leaching conditions tend to be on very light soils and after high rainfall events as well. There's also evidence to show that there could be pollution swapping occurring when using nitrification inhibitors. Because we see more nitrogen remaining in the ammonium form, it's therefore more vulnerable to volatilization. So there's limited evidence in the UK to suggest that we see more volatilization with use of nitrification inhibitors, but it is worth bearing in mind and considering when using these products. So in the same way as I did with the urease inhibitors, we can quantify the impact of using nitrification inhibitors on the carbon footprint of a crop. There's little activity data, as you can imagine, in the UK on using nitrification inhibitors with nitrogen fertilizers on farm because of the fact that I mentioned that they have little agronomic benefit. But based on past research and field trials, we can apply a reduction factor of around 44% to those direct nitrous oxide emissions if a nitrification inhibitor is being used. So using this reduction proportion, we can quantify the impact on the greenhouse gas emissions using the example winter wheat feed crop I did previously with a total nitrogen rate of 200 kilos. So I've taken two examples, ammonium nitrate and urea. So without the use of a nitrification inhibitor, the direct greenhouse gas emissions from those nitrous oxide emissions are around 445 for ammonium nitrate and 346 for urea. Taking this 44% reduction, this reduces to 250 and 195 with the use of a nitrification inhibitor. And the impact that has on the total carbon footprint of the crop is quite significant because of the fact that these nitrous oxide gases have a high global warming potential, and therefore, as Ben showed in his pie chart, they contribute a lot to the carbon footprint of the crop. So by reducing these direct nitrous oxide emissions using nitrification inhibitors, we can contribute to a 10% reduction and a 7% reduction for ammonium nitrate and urea use on the total carbon footprint of the crop. So before I finish today and hand back over to Pete, I wanted to talk about work that's been done to understand any negative environmental impacts on using urease and nitrification inhibitors on the soil biological communities. So considering urease inhibitors, specifically agrotane, this product has passed extensive US EPA toxicology and environmental tests, and past studies have shown that it has a temporary impact on the soil as it degrades after around 10 to 14 days after application, and it degrades into the fertiliser elements nitrogen, phosphorus and sulphur. In terms of nitrification inhibitors, you could argue that there's more work to be done in terms of fully understanding any potential negative impacts on the soil biological communities, but work that has been done has shown that nitrification inhibitors have a temporary impact on nitrifying bacteria with a limited impact on non-target soil microbes. So previous work has shown low or no toxicity to soil fauna such as earthworms, and a more recent long-term study in Ireland in a grassland environment, which tested both urease and nitrification inhibitors, found no impact to non-target organisms. So I'll hand back over to Pete now, but I hope that gives a nice summary of the activity of urease and nitrification inhibitors and their value to reduce greenhouse gas emissions associated with nitrogen fertiliser.
Thanks very much, Christina. And thank you to all for putting the questions in the chat. We're sort of trying to answer a few of them as we go along. We'd like you to answer a poll now to help us decide what the next webinar should focus on. So the first question is, do you want to learn a bit more about nitrification urease inhibitors? And if you could answer that, that'd be good. And then we move on to the next poll, which is more specifically, what types of areas do you want to learn about? Do you want to learn about certain types of crops, such as grassland and forage crops? Or do you want to learn about the use of these inhibitors on specific arable crops, such as maize, for example? Do you want to learn more about the regulation side or environmental effects or specific products? Manures is another important area, of course. In this webinar, we deliberately focused on inorganic fertilizers because we felt it was maybe a too large a topic to cover in our time allocation to include manures, but potentially manures is a very important area that we could focus on in a future webinar. So if you could rank those options. I'm just doing it at the same time myself so I can sort of give a feel for how long it takes, because I know that ranking these things takes a while when you've got several options to focus on. So I'll give you a few minutes really to sort of get the order of these right, because it's really helpful for us to know what to focus on in our next webinar. I'm really pleased that so many of you are keen to learn more about the inhibitors. That's good news. So probably another webinar on this topic will be useful. I mean, you've seen that nitrogen fertilizer represents the largest proportion of greenhouse gas emission sources, so it's a really important area, and these inhibitors do contribute significantly to reducing those greenhouse gas emissions. So I think careful use of these inhibitors is really important for helping us to achieve some reductions. Okay, I'll give you a few more seconds to finish off ordering those options, and then we'll move on to the next slide. Okay, but if you move on to the next slide, please, Christina. So we now move on to our Q&A session, and if anybody wants to ask a question verbally, then please raise your hand, and Ben will unmute you. Alternatively, just put another question into the chat and we'll do our best to answer them. And if anybody else has answers to these questions, don't sort of assume that we at ADAS know everything and got all the answers. Then please, put your answers in as well, because I know there's lots of researchers on this call who will have knowledge which is going to be really valuable for the rest of us on this call. So we've already had a few questions. One of the questions was about the type of urease inhibitors, as to whether we have any information on other urease inhibitor types, thiosulfate and MCDHS. For the UK, we haven't done any work on those specific urease inhibitors. We've focused a lot on MBPT and the other two products that Christina described. But if anybody else on the call has got experience with thiosulfate and MCDHS, then please put your sort of knowledge into the chat to help us all. We've then had a question about how widely nitrification inhibitors and urease inhibitors are used by farmers. At least in the UK, they're not that commonly used, but they are increasing quite rapidly in the UK. Especially urease inhibitors as a result of the voluntary initiative to minimise ammonia emissions associated with urea use. So the use of them in the UK at least is certainly increasing, but it's increasing from a relatively low level. Then got a Yeah, thanks, Paul, for answering the question about numbers of farmers. Yeah, not many. Good. I'm glad we agree. Impacts on yield. Again, my colleague Paul Price has answered this question, but just to sort of reiterate, what are the impacts of urease inhibitors and nitrification inhibitors on crop yield? For nitrification inhibitors, there's little evidence of impacts on yield. I think you have to remember that the amount of nitrogen lost from the fertilizer product as nitrous oxide, is only in the order of 1% or even less. So reducing that makes a really useful reduction in greenhouse gas emissions, but agronomically, it's not going to make a huge difference to the yield. So we haven't seen impacts on yield from nitrification inhibitors. We do see impacts on yield from the use of urease inhibitors, as Christina described, particularly in situations where there's large amounts of volatilization. I'm just picking a question which to focus on. Perhaps I could just ask a question to Christina about the commenting about why no-till might affect the nitrogen release more than using, say, conventional tillage.
Yes, that's primarily down to the fact we tend to see slightly higher compaction in the surface soil. So when the fertilizer is applied, there's less fertilizer to soil contact, so it's tend to see slower breakdown of the fertilizer, and therefore it sits on the soil for slightly longer and is more vulnerable to volatilization. But there's also evidence to suggest that the greater levels of trash on the soil surface can increase the soil temperature as well, and contribute to conditions that can increase volatilization. So I think it's an area that needs more research, but there's been work that's done to show associations with higher emissions in no-till scenarios.
Yeah, thanks, Christina. I can see you've also got a question about whether the 44% reduction in nitrification inhibitors is related to the sum of direct N2O emissions and indirect N2 emissions as a result of leaching.
So the 44% reduction is relevant to UK conditions where we don't tend to see an impact of nitrification inhibitors on leaching. So this is primarily a reduction in the direct nitrous oxide emissions.
Yep, thanks, Christina. I can see a question from Mark Hemmant about use of nitrification inhibitors. You don't need to answer this, Christina, because you might not know the answer to this, but I'm just sort of putting it out there, really. What are the agronomic benefits from nitrification inhibitors in leaching-prone situations? I mean, I've been aware of some research done in other European countries with maize, where nitrification inhibitors reduce the amount of leaching in a wet spring. So there could be some potential there to reduce nitrate leaching. I think there's a lack of evidence on this as well, really, in that nitrate leaching isn't the easiest thing to measure ever. So experiments on this are not that commonly done. So we probably need a bit more information on this area. We've got another question here from Michael Brennan. If urea treated UI is applied in dry weather and doesn't get absorbed into the soil for 14 days, will the UI still be effective in reducing ammonia emissions? I'm not sure whether we know that, do we, Christina, for sure. Certainly in that sort of situation, the risk of volatilization is going to be pretty high in those sorts of environmental conditions. But I would have expected the urease inhibitor to be active for quite some time.
Yeah, I agree. We couldn't quantify the exact impact of the urease inhibitor in that specific scenario, but because volatilization conditions are high, you'd assume that the inhibitor would have a larger benefit in those greater volatilization conditions. But it's difficult to say over a certain period of time.
Yeah.
But there is work that's been done to show how environmental conditions also impact the efficacy of the inhibitors themselves. So if we did do a later webinar, we could focus on conditions which impact the efficacy of the inhibitors as well.
Yep. Thanks, Christina. Okay. Well, there's a number of questions there. There's one or two we haven't answered, but we've answered quite a lot there. We'll check what we haven't answered and circulate some answers where we can provide those answers in due course. We'll have a look at the polls to see what we should focus on in a future webinar. But I'll draw this webinar to a close now and thank my speakers, Christina and Ben, and my colleague Paul Newell-Price for answering so many of those questions. Thank you, Paul. Thank you for putting the questions in as well. It makes for a very interesting interactive webinar there. And we will be in touch with a future webinar focused on the things you want it to focus on. So thanks again and have a good afternoon.